metal nanocluster metamaterials.
My name is Tiu. I'm from Boulder here, Electrical Engineering Department. Today I'd like to talk about our studies on these nanocluster-based metamaterials. This study is done together with my colleagues Tim Lee and Tian, and also my advisor Wan Yi. Here is the outline. I will first introduce these metamaterials, and then I will present our designs of optical frequency magnetic metamaterials based on those metal nanoclusters. Those materials will exhibit negative permeability, negative mu, and therefore can be used to construct negative index materials. And I will show you two of our negative index materials designs based on those nanoclusters. In the second part, I will show some of our experimental realization of those magnetic metamaterials use gold nanoparticles self-assembling. And finally is the conclusion. And we just heard a great introduction on metamaterials from Professor Shen, so I think this will make my explanation much more easier. So metamaterials are those artificial materials whose optical properties can be engineered by properly designing your structure unit. And usually those structure units are much smaller than the wafers. And they allow us to design for these unconventional properties such as negative index. And because of their special properties, they opened some new applications, super lens, we just heard about, and also this cloaking effect. Actually here in this movie, I just showed electromagnetic simulation of a two-dimensional cloaking, which is shown in this shell region here. As you can see, because the existing of this cloaking device, an instant plane wave can be guided through this cloaking region, and it's not going to interact with whatever object inside here. And on the second part, the plane wave wavefront is preserved after this cloaking, and you can see there's almost no scattering from here. And this is the idea of this invisible coming from. And one way to achieve negative index materials is to have simultaneously negative permittivity and permeability, epsilon and mu. It is relatively straightforward to have negative epsilon using those metals, but it's actually challenging to have a magnetic active material, especially in optical frequency region. So to have magnetic active materials is an essential part in this metamaterials research. Since the first demonstration of this split ring type of metamaterials, there has been intensive research going on using various types of metallic resonance structures, and we have seen a lot of, from the previous talk, like these fishnet structures. Actually, there is an alternative approach to achieve magnetic activity that is using this Mie resonance. So the basic idea is shown in this schematic here. As you can see, in a single dielectric cylinder, we can have an induced magnetic dipole momentum, which is caused by a resonant displacement current. So those localized magnetic Mie resonance can then be used to create an effective medium that has a resonant in mu when you have a periodic array of these cylinders. In order to have negative mu, you need to have a strong magnetic resonance, and that requires those cylinders to have a high dielectric constant. Therefore, people have demonstrated using ferroelectric materials and fluoronic materials in the microwave and infrared frequency region. So what we want to see is magnetic metamaterial in the optical frequency region. So we studied metal nanowires and nanoclusters. So a periodic array of metal nanowires, also called plasmonic crystals, have been shown to exhibit a resonant behavior in effective epsilon when it is excited by a so-called transverse electric field. So this picture actually shows the calculated effective epsilon of a square array of silver nanowires shown here. As you can see, the red curve shows the real part of the epsilon, and it is indeed resonantly enhanced. So now you can consider have an effective medium that has a high dielectric constant in this optical frequency range, and then you can use this effective medium to create the cylinders I just showed in the previous slide, and that's we refer it as a nanocluster. So this movie actually shows the resonant magnetic field supported by this cluster, which is composed of 7 silver nanowires. And those field is localized as I just shown. And we can imagine using those nanoclusters as a construction unit cell. We can build a magnetic metamaterial by having a periodic array of these clusters, as I will show in the next slide. And actually before that, one question is, since these clusters has a finite number, actually just 10 or 20 of these nanowires, is it okay to call it as an effective medium? In order to answer that, what we studied is we calculate the scattering properties and compare the scattering property of a cluster and a homogeneous material which has an effective dielectric constant that is same as the infinitely large silver nanowire array. So this is showing the calculated scattering efficiency between a real cluster and this imaginary homogeneous material, which has the same size and dimension. And the red curve is for this cluster. As you can see, they match pretty well in the low frequency range, which shows that we can actually consider such a cluster as an effective material. In other words, it's artificial fluoronic material because of these dispersion properties. And another feature is they both show a strong scattering peak, which is corresponding to a magnetic Mie resonance as shown by the magnetic field patterns here. So indeed, we can use those clusters as our building cells. Now we use these clusters and assemble them together into another theoretic array. In this example, it's a square array. And the Mie resonance frequency is here, and the excitation field polarization is indicated here. Once we do that, we can calculate the effective mu of these artificial materials, which is shown here. You can see the real part of this mu demonstrate Lorentz type of resonance, and it indeed go to negative within this frequency range. And this frequency, I want to point out, is exactly this Mie resonance frequency. This indicates the the resonant behavior in this effective mu is coming from the magnetic mirror resonance of these individual nanoclusters. In order to see whether this effective meaning description of this nanocluster array is valid or not, we also perform a photonic band structure calculation because we are having a periodic structure. So the blue curve in this figure shows the calculated photonic band structure, and you can see there is a photonic band gap opened here. I want to point out this is not due to the normal bright refraction because it actually occurs at higher frequency. And what causes this photonic band gap is the negative mu, so that the electromagnetic field will essentially decay in this material, so you don't have propagating wave, and that's why you have a photonic band gap here. And also, another comparison you can do is you can actually calculate your dispersion properties of your material using this formula. And since we already have the effective parameters, the epsilon and the mu of this material, we just plug it in and plug it as shown in the red curve. You can see there is a good agreement between this blue and the red curve. One of them is calculated by solving the eigen mode of this photonic band structure, and the other one is simply using this formula. And this actually shows it's valid to use the effective meaning description to describe our magnetic metal material. Now we have these magnetic metal materials using these nanoclusters. We can then construct a negative index materials by combining those nanoclusters with other components that give us negative epsilon. And the first example is because metal exhibit negative epsilon below the plasma frequency, we sandwich these nanoclusters between two thin films of silver, and this is actually the unit cell of our negative index materials. And by calculating the transmission and reflection curve, as already shown in the previous talk, we can extract the effective parameters of this material. The blue shows the real part of the mu, and the purple pink shows the real part of the epsilon. So you can see within this frequency range, you have simultaneously negative epsilon and mu. The epsilon, negative epsilon come from the silver field, and the negative mu actually comes from the nanocluster. And therefore, you have a negative refractive index within this frequency range, which is shown in the blue curve here. And the negative index in this particular case can reach -1 at this frequency. And people always use a figure of merit, which is basically the ratio between the real and the imaginary part of the refractive index to characterize the properties of the metal materials. And in this case, they reach a maximum number of 2, which is actually similar to other types of negative index materials such as fishnet structure. And an alternative way to realize a negative index materials is to use, other than the plasma response of a metal, use the electrical resonance of those so-called coated nanowires. So as an example I showed here is this is the same nanocluster I just used before, and those guys are silver-coated silicon core nanowires. So the red color actually represents silver. And again, we use the same technique to calculate the effective parameters. As you can see, both the epsilon and the mu shows a Lorentz type of resonance, and the negative epsilon, which is this curve, covers that of the negative mu, and again you get simultaneously negative epsilon mu in this frequency range, and also you get negative index at these frequencies. And we showing this because we are using these just different types of nanowires, and we can imagine this type of architecture, which is composed of basically just nanowires of different type, and the analog three-dimensional structure that is composed of nanoparticles or nanoshells. It's make it suitable to use the bottom-up fabrication techniques such as self-assembly. And indeed, we've shown that this magnetic metamaterial scheme can be extended to three-dimensional structures composed of nanoparticles and nanoshells. So as an example I show here is a nanocluster composed of 8 gold nanoparticles forming this cubic kind of structure, and it supports magnetic resonance at visible wavelengths. And our group has also studied different types of clusters of nanoparticles that support this magnetic resonance. And we believe this is a practical platform to realize these optical frequency magnetic metamaterials. So we use this gold nanoparticle cluster self-assembled on this pattern substrate to realize our magnetic metamaterials. So first we synthesize gold nanoparticles with diameters of about 14 nanometers by using the reduction reaction, and then we stabilize them in the solution by subsequent coating. And in the meantime, we prepare a two-dimensional patterned structure by using laser interference lithography, and this schematic actually shows the optical setup of this experiment, and here is an SEM picture, shows the fabricated 2D patterning on SU8 photoresist. Once we have these two, we can do the self-assembling by putting the solution on top of this pattern substrate. As the solution is dried, the gold particle will be driven into these nanoholes predefined by the lithography due to the capillary force of water. And the undesired particle deposition outside the holes can be suppressed by treating those areas with RE. And in this way, those gold nanoparticles can be self-assembled into each nanohole and form a nanocluster. And at the same time, the predefined pattern actually form the nanocluster array. So those SEM pictures shows the fabricated nanocluster arrays with different size and periodicity. So in order to characterize those magnetic metamaterials, we perform this transmission reflection type of measurement. And we do the normal instant light and then record the transmission and the reflection. And here is one example of a measured absorption spectrum of such a material. You can see there is an absorption peak at these wavelengths, and we find that this is actually due to the magnetic resonance of the material. So in order to conform or compare the experiment result, we also perform the numerical studies. This is actually a two-step process. First, because we have a large number of nanoparticles this time in the nanocluster, we use the effective medium theory to calculate the effective epsilon of each nanocluster. And this is shown in this figure here, and you can see again there is this effective epsilon resonance. And after that, we use this effective epsilon and perform a full-wave frequency domain simulation, and we calculate the transmission and reflection spectrum of these nanocluster arrays. And then from there, we can retrieve the effective parameters. And here shows one example of the calculated effective mu, which again shows this Lorentz type of resonance, and it goes to negative in the optical frequency. So here shows one example of the comparison between our experiment measurement and the calculation. Here is the measurement absorption spectrum for the same pattern periodicity but different cluster diameters. The blue is the smallest one, and you can see the absorption peak shifted to the longer wavelengths as you increase the size of the cluster. And indeed, to each other, you can see the absorption, calculated peak associated with longer wavelengths. And also from the calculation, we notice this absorption peak is indeed due to the localized magnetic resonance, as can be shown by those magnetic mode patterns. This is a magnetic dipole resonance here. So finally, I want to conclude. We present this new metamaterial architecture based on these nanoclusters, and they exhibit negative mu in optical frequency range, and they can be used to construct negative index materials by combining them with other components. And because this resonance is fundamentally due to the plasmatic resonance of the particles, so they show the resonance in the optical frequency range, and that's what we can achieve metamaterials in this frequency range. And also, because of the materials is composed of these gold particles, and they are compatible with the self-assembly fabrication techniques, and we believe this is a promising metamaterial architecture for realizing optical frequency metamaterials. So with that, I'd like to thank you.
Quick question. Okay, well, no, I don't think I'm equipped to ask it.